At its core, trigonometry is the study of triangles. Even though a triangle may seem a very simple idea, there's a lot of unique and interesting properties that we can explore and use, as you will find throughout this class. Triangles are very predictable when it comes to measuring its sides and angles. This makes it invaluable in indirectly measuring distances that normally wouldn't be possible. For instance, have you ever wondered how far you can see over the ocean while standing next to the water? Trigonometry tells us that it's approximately 3.1 miles. You'll see later on how exactly that is arrived, but that's just one of the many applications that you can use. I'd like to take a moment to show you a demonstration video which shows you a basic difference between the triangle and the rectangle to kind of give you more of an idea as to why triangles are so important to us.
Hello, welcome to Trigonometry. I am so excited to teach this class, and I hope that you're excited to take the class. Trigonometry is one of my favorite subjects, and not because that I just really like math. It's a very applicable mathematics, and you can use it in your daily lives, and you could probably find some place that you could. You may not, and I totally understand that. You might not gain my affinity for triangles, but that's okay. I hope that you do find something that you could use along the way. A couple things that I'd like to talk about with triangles. First off, why triangles? Why do we have an entire class dedicated to the study of triangles? Why not squares or circles or any other object? Well, it turns out that triangles have all kinds of unique properties for such a simple object. So we're going to investigate some of those. Today, I'd like to show you something that I find that's really interesting about triangles, and that it's a rigid object. Now, a rigid object is an object that cannot be deformed. So let me show you what that means. This is a square, obviously, and this square is not a rigid object. And I've set things up so that the cards are stacked against it. And I have 4 sticks basically connected together with circular dowels, just a single circular dowel, so that if it's going to deform, this is going to be the easiest thing to deform. So if you'll watch, there's probably no surprise that it is very easy to deform this square and change its shape. Now, let's look at a triangle. I have the exact same setup. I have 3 sticks now, joined together by single circular dowels. But a triangle is a rigid object. No matter what I do, I can't deform the triangle. The best hope I have is to just apply enough pressure to actually break the triangle. But I can't deform it on its own otherwise. The square, it's very easy. I could make the square stronger. For instance, in a house, we often put additional bracing, in between, and that'll keep it from deforming. So that'll help. You could also change the way that we've connected the endpoints of the square together, make it stronger. But with a triangle, none of that is necessary. It's already a very strong object just because it's a triangle. And that makes it very important architecturally. So for instance, if you are ever downtown Charleston and near the music farm, that's a fascinating building to me because inside there is a huge span of very large roof, and there's no supports all the way across from either side. And there is nothing but wood and bricks being used to build this. The span being so long for the roof, you couldn't just have straight pieces of wood. You probably couldn't find any long enough, and if you could, they would sag in the middle and break over time. But in order to make the roof so that you wouldn't need any supports in between, the architects chose to use an arch. And an arch is generally based off of a parabola, which is another type of very strong architectural structure. But that parabola, that arch, it is made up of individual triangles. So if you look very closely, you'll see a group of triangles over and over again that make up the strength of the roof of that building. It's fascinating. Where I grew up, another example, is in West Virginia, and the most famous bridge in West Virginia is the New River Gorge Bridge. The New River Gorge Bridge, if you have a look at it, it is a bridge that spans between two mountains from one side to the other, and there is no supports underneath other than, the side of the mountains itself. The way that the architects designed it, the base structure is a parabola, again, a very strong object architecturally, very important. And so there is a parabola that makes up the base. But that parabola is made up of steel structure of triangles. You can break it down and you can see the individual triangles, and that is where the strength of that structure comes from. So it allows the bridge to span a huge distance without any additional supports underneath. And I am using an equilateral triangle. You might be thinking, well, this is something that is inherent to equilateral triangles. It isn't. Here's an isosceles triangle. The isosceles triangle has the exact same property. I cannot deform, no matter what I do, the isosceles triangle. The best I could do is just break it. The isosceles has two sides that are equal. The equilateral has three sides that is equal. The scalene, which I have next, has no sides that are equal length. Still has the exact same property. The idea is, when I try to deform, this angle right here, these two sides, this side and this side, are locked in place by the length of this side. It can't move because of that side's length. And if I change and look at a different angle and I try to deform that angle, this angle is locked in place by the length of this side. When it comes to a square or a rectangle, that's no longer the case. So if I try to deform this angle right here, it's not locked in place from this point to this point. It's not locked in place at all. I can easily move. Something else has to change equally on the other side, but I can make that deformation. I simply can't with a triangle. And that is something that I find absolutely fascinating about triangles.
Before we begin our study of trigonometry, we have to go through a basic geometry review. Starting with some terms, we'll begin with a point. A point is a location in a plane or space and is usually labeled with an alphabetic name such as A, B, C, etc. And it's important to understand that the point doesn't contain any mass or area or any sort of measurement whatsoever. It's just a location in the space. A line is a straight one-dimensional figure having no thickness and extending infinitely in both directions. Two known points are required in order to uniquely define a line in a plane. It's common to use the name of these points to name the line, i.e. AB, if those are my points that it's passing through, and then a small line above it. And notice there's arrows on both ends of that. However, it's also common in an algebra course to label lines as L1, L2, etc. A segment. The portion of a line contained between two points, but not extending past those points. We label it with the points that it's going toward as well, just like the line. And we put a line above it, but there's no arrows on top, indicating that it's not extending past those points. A ray is the portion of a line that begins at one point and extends through another point, and continues on to infinity, which is labeled AB, the points that are, the line is, that tell you the direction of the line. A is the beginning, and then B is the point that you're passing through that you're going on to infinity. So for example, given 2 points A and B, the line that would be passing through the points A and B would look like this, and extending through both points, going on to infinity in both directions. The segment using the points A and B only contains the portion of the line between those points, and the ray starts at point A, passes through point B, and continues on to infinity. Angles. Most commonly, an angle consists of 2 rays joined together at a common endpoint. However, an angle can be formed by 2 intersecting lines or 2 segments with a common endpoint as well. One ray is called the initial side of the angle, and the other ray is called the terminal side of the angle. The common endpoint of the rays is called the vertex of the angle. Angles in geometry are often labeled using the 3 points they pass through, such as this symbol that kind of looks like an L. You read that as angle, and then you have the points in question. The middle point is your vertex. What happens though, when we are doing work with trigonometry, we often have to label a lot of angles, and it just gets messy using this type of notation. So in trigonometry, we often use Greek letters to represent angles. Most commonly, we use the Greek letter theta, although it's common if we need multiple angles to use the Greek letter alpha, beta, or even gamma. So those are some letters that you'll probably start getting used to as you move through. But there's nothing special that they're Greek. It just simply, there are so many letters that are predetermined as to what they're measuring in mathematics, like the lowercase letter m generally represents slope. When you get so far in mathematics, you kind of run out of the English alphabet. So the Greek alphabet, is just some additional characters that we can use to label things. And this is what an angle would look like. You have its initial side, the terminal side, and your vertex. So if it's passing through, let's say this is point B, and the vertex is point A, and this is point C over here, then we could label this angle as angle BAC. And as I mentioned before, the middle letter here is the vertex. Another way to notate this, to use the Greek letter notation, you could label this as angle theta. Just put a theta in here as well. Notice I demonstrated which side is the initial and which side is the terminal through this arrow that I've drawn. The arrow only has one endpoint, and the other endpoint is the start, so you don't have to label what's your initial side and what's your terminal side every time. You know that the part that has the arrow is your terminal side, so you know which way the angle is rotating. Measuring angles. Angles have many different ways to be measured. Some of the more common measurement systems are degrees. So the Babylonians defined there to be 360 degrees in one revolution of a circle, probably because it took about 360 days before the same constellations started showing up in the same part of the sky each year. Degrees are probably the most common measurement of angles. And we're very used to the idea of degrees, most of us are, and so they seem natural. There's really not much natural about them at all. Obviously there's 365, and a little bit of change there. of days per year. And so using 360 is really just a trade-off between the number of days in a year versus a number that has a lot of divisors in it. So, there's nothing really natural about that set of numbers. It's just they seem natural because we're used to them. A more natural system are radians. This is a unitless measure of angles that depends on the ratio of the circumference of a circle to its radius. It sounds very complex, but it has a lot of advantages, and we'll see some of the advantages in the next unit when we start looking at radian measure in detail. Revolutions. This is a measure of a full rotation or a cycle. So for instance, automobile engines are generally measured in revolutions per minute, so RPM. I'm sure you've heard that term. So this would be a measure of going through an entire circular motion a number of times. Slope. I'm certain that you've heard of slope if you took an algebra course. It's a very common system there to measure the direction of a line. But essentially, as we'll see through this course, that is basically a direction based off of an angle. If you've driven on the interstate, you've probably seen measurements of grade. This is a type of slope that measures the amount of vertical incline or decline to a horizontal distance of generally in feet, so 100 feet. And it's usually given as a percentage. So if you're driving on the interstate and you see a sign that says, there's a 10% grade ahead, that means for every 100 horizontal feet that you travel, you're going to go down 10 vertical feet, or up 10 vertical feet, as the case may be. One that's particularly uncommon is the system of gradients. It was a system developed by the French. It's similar to degrees, but it uses 400 gradients in one revolution of a circle. It's rare that you see this anymore, but sometimes you'll find it in surveying applications, which is why I mention it, because any of you going into engineering, you may run into it at some point. It was basically designed because 360 is just a kind of a random number to use for the number of degrees in a circle. 400 works just as well and has a few more advantages. It never really caught on. Occasionally you'll run into a old scientific calculator that has 3 different modes for measuring angles: radians, degrees, and grad, standing for gradients. Most people didn't know what that was even for anyway. In geometry, we allow a positive angle measure. We only allow positive angle measures between 0 degrees and 180 degrees. And we label those as acute, right, obtuse, and straight. An angle measure is acute if it's between 0 and 90 degrees. It's right if it's equal to 90 degrees. It's obtuse if it's between 90 and 180 degrees. And a straight angle if it's equal to 180 degrees. So that you can visualize this, I have an applet that you can play around with. It'll be available to you in the class. Any of these applets that you see through the videos will be available to you. But this applet, it gives you 3 points and 2 segments joining to make an angle, and it tells you the angle measurement. And you can move any of the points around, and it will tell you what angle measure you have for you. But not only that, if you'll notice, it tells you if you have an obtuse or an acute, and actually if you are able to hit it just right, there we are. You can get a right angle or a straight angle out of it as well. So it'll tell you the type of angle that you're working with. So acute angles from 0 to basically 89 degrees. Well, actually up to 90, but not including 90. Then at 90, you have a right angle. And then from from 90 over to 180, you have obtuse angles until you get to an 180 exactly. If I could get it just right. Bear with me. There we are. You can get a straight angle, which is basically a line. And that's fine. You can have that sort of thing. Now, in geometry, there's not a whole lot of reason to do anything larger than 180 degrees. So if you continue rotating C around, what you'll notice is it just starts measuring the smallest angle instead of measuring this angle as 180 degrees and larger. It just switches and starts counting downward at this point as I continue rotating. This applet will let you move any of the points, and you can kind of play with, and it'll tell you, if you have a right angle, obtuse angle, or whatnot. But that's how geometric angles work. Trigonometric angles. In trigonometry, there are no default restrictions on angle measures. So you can have angle measures that, are thousands of degrees, millions of degrees. Anything from negative infinity to positive infinity can count as a valid angle measure in trigonometry. It also can be positive or negative as well. In most applications, however, it's customary to restrict your angle measures to between 0 and 360 degrees. In terms of positive angle measure and negative angle measure, if you have an angle that rotates counterclockwise, it has a positive angle measure. So if I rotate counterclockwise, then the angle measure that makes is greater than 0. It's positive. However, an angle that rotates clockwise has a negative angle measure. So this angle measure theta would be less than 0 of some sort. An angle is said to be in standard position if the vertex is located at the origin and the initial side is located along the positive x-axis. In this setup, the terminal side can be located in any of the 4 quadrants or along an axis, which is referred to as a quadrantal angle. The angle measurements of quadrantal angles then are 0, 90, 180, 270, and so forth. And I have another applet that I'll show you here that'll let you play with standard position angles. Okay, so this applet will let you take a look at what happens with angles in standard position. So the vertex here is always going to be at the origin, and this initial side here will always stay along the positive x-axis. The only thing that I can move here is the point P, but as I move it, you'll notice that the angle measure theta changes. And theta can go between 0 to 360 degrees when it finally wraps back around and starts recounting back at 0. So it won't let you go any larger than 360. If you rotate negatively, it still will keep you in the bounds of 0 to 360. It won't. This applet won't go into negative angles. But what it will do is when your point is in a particular quadrant, and the quadrants that I'm talking about, back in algebra, you learned that quadrant 1 is where x and y are both greater than 0. Then this is quadrant 2, this is quadrant 3, and this is quadrant 4. So the same quadrants that you had back in algebra. The quadrant 2, x values here are less than 0, because if you look along the x-axis, notice I have negative numbers labeling on the x-axis, but the positive y. So y is still greater than 0. Any point that's in quadrant 3, the x's are less than 0, and the y values are less than 0. And any point that's in quadrant 4, the x is greater than 0, but the y is less than 0. So depending on the signs of your x and y values, you can define what quadrant you're in. But not only that, you can also define what quadrant you're in based off of the angle measure. So quadrant 1 has angle measures between 0 and 90 degrees, which is what it's telling you right here. When you get up to exactly 90 degrees, you run into what's called a quadrantal angle. And a quadrantal angle is an angle that's lying directly on one of the axes. All right, we'll pass this angle and we'll go on into quadrant 2. Quadrant 2 angles are measured from 90 to 180 degrees. But then when you hit 180, you come across another quadrantal angle where theta is equal to 180. As you continue rotating, you're now in quadrant 3, where all of your angle measures are between 180 and 270, until you get to this next quadrantal angle, where theta is equal to 270. And you can continue rotating. Quadrant 4, values are between 270 and 360, until you get here, and this app will tell you, let you use theta as 360 and theta as 0 for quadrantal angles. It's just a boundary issue, but that's okay. It's the same angle. Whether it's 360 or 0, it's still the same angle measure. So that's how angle measures in standard position work. Supplementary and complementary angles. Two angles whose sum is 90 degrees are called complementary angles. And two angles whose sum is 180 degrees are called supplementary angles. I'm not so concerned with you knowing the definition of these terms. I'm more interested in you just understanding the concept here. Let me show you some supplementary and complementary angles on an applet. So complementary angles are two angles that add up to 90 degrees. So what I have in this applet is you can move point A around, and no matter what, if this is, we'll say theta 1, and this is theta 2, if you'll notice, those two angle measures together make a right angle, no matter how I change where point A is. So always is the case that whatever, theta 1 is, in this case it's 26 degrees, and theta 2, they're going to add up to 90 degrees, which is what this is indicating to us over here. So you can have any sort of angle measures between 0 and 90 that will work. This applet will actually let you go out of bounds. It doesn't make any sense when you go out of bounds, so you need to stay within 0 to 90. But if you stay in that range, you'll always have two angle measures that add up to exactly 90 degrees, and those are complementary. And again, I'm more interested here in you understanding that if you have two angles that form a right angle and you know the measurement of one, you can always find the other by subtracting from 90. Same thing for supplementary angles. Supplementary angles are two angles that add up to 180 degrees. So basically, if you have, two angles that together form a line, and you know one angle, you can always find the other one by subtracting from 180. But I'm never going to test you on knowing the definition of the term supplementary versus complementary. It's just the concept of that, which is what I'm looking for. So to give you an example of what you might see in the homework, for instance. So find the measure of each angle in the following situations. So in this first situation, I clearly have two angles that are forming a right angle, so their angle measure is 90 degrees. And because of that, I can say that the sum of those two angle measures is equal to 90. And this gives me a pretty simple linear equation that I can solve. So for instance, 2x and 3x are like terms that can combine into 5x. 6 and negative 1 can combine into 5. Now, the next step in the process, if I subtract 5 from both sides, oops, I'll do that like this, then I'd have 5x equals 85. And then I need to divide both sides by 5 so that I find x is equal to 17. So x is equal to 17. So the angle measures, neither one of them is equal to 17. 17 is just the value of x. So in order to figure out what the angle measures are, I would need to take 17 and plug it in for x. So if I did 3 times 17 minus 1, for instance, that would give me 50. So that means that this angle measure is equal to 50 degrees. And this angle measure, when I plug in for x, 2 times 17 plus 6, that's 40. And if you'll notice, 50 plus 40 does in fact equal 90 degrees. So it works out just fine. Okay, the next example, let me move my calculator over, is this. I have two angles that are forming a straight angle. And what I would know about that is the sum of those two angles is 180 degrees. So it's a linear equation, combine like terms. So 3x and 6x is 9x. If I subtract 18 from both sides, then I have 9x equals 162. And if I divide both sides by 9, I find that x is equal to 162 over 9, or 18. And again, that doesn't tell me what the angle measures are, but I can use that to find the angle measures. So for instance, 6 times 18 plus 18 is 126. So this angle measure over here is 126 degrees, and then 3 times 18 gives me 54. So this angle measure is 54 degrees. Degrees, minutes, and seconds. So degrees, minutes, and seconds is a system where we try and make angle measures more accurate. You see, the issue is 360 degrees is it's useful for very short distances. But when you start looking at navigational applications or astronomical applications, you start to find that they're not as accurate as you need them to be. So for instance, I'm going to pull up Google Maps and I'm going to show you something quickly here to indicate what I'm telling you about here. Okay, so what I did is I just basically found the latitude and longitude of the Charleston Harbor as a midpoint and found that it's 32.74 degrees in latitude and negative 79.86 in longitude. Now, I looked for across the ocean a place that was on the same latitude. So if I zoom out here, make it easier to get across. I'm gonna keep zooming there. Gosh, there we go. All right, so I basically found if you stayed on the same longitude, it puts you in practically in Morocco. Although strangely enough, there's a little island that you would run into for this experiment, but that's okay. We'll pretend like that's not a problem. All right, so in Morocco, gotta really zoom back in here again. Yeah, here's the place. So I'm not even gonna pretend I can pronounce the name of this, but basically there was kind of a bay near this area, which was on basically the same latitude. So it was in this case 32.74 degrees again. Oops. And longitude was negative 9.04. It's a different place, obviously, so the longitude changes, but it's on the same line. So I basically checked into the distance here. So how far away, these two places are. So it turns out that the distance is about 6,500 kilometers, approximately. So if you travel from here straight across, about 6,500 kilometers. Now, the question is, let's say you're supposed to travel straight that distance. If you're off by 1 degree, what kind of range would you be if you missed your target by 1 degree versus 1 minute or even 1 second? So how accurate do we need to be with this for navigation? Well, zoom back into Charleston here. Okay, that's good there. Zoom out a little bit. All right, so it turns out that if you're aiming for this point right here, and you're off by 1 degree, that would basically put you somewhere between Hilton Head and Murrells Inlet, which is a range of about 113 kilometers difference. 113 kilometers each way. So if you're off by 1 degree, that's pretty significant in terms of where you're actually going to end up landing. You may not be able to recognize what place you're in. If you are off by 1 minute, however, we can zoom in on this one. It turns out you're in a lot better shape. It is somewhere, it's a 2 kilometer difference. Oh, my point didn't move. I guess I should have expected that. But it's a 2 kilometer difference, which basically puts you, somewhere around Morris Island and somewhere on Sullivan's Island. And that's pretty good, just being off by 1 minute. So navigationally, the minute should be just fine. The second is about 1/3 of a kilometer, which wouldn't even put you at the edges of the port. So the second, if you were accurate to the, within 1 second of where you wanted to be navigationally crossing the Atlantic, that's accurate enough to really get you where you need to go. The need for more accuracy, so navigationally across the globe, degrees, minutes, and seconds works great. But let's say you're looking at interstellar distances, then the second could be off by still a great deal when you look at the differences between how far apart planets are. So we'll look at that in a little bit, but within the globe, degrees and minutes and seconds are accurate enough. But when it comes to actually working with degrees, minutes, and seconds, there's not really much that I want you to be able to do except for use the calculator to get around them. The textbook explains a way of converting them manually, but you're not going to need to be able to do that. So let's look at a couple of examples of what you would be expected for the homework, for instance. So convert the following to degrees, minutes, second format. So 38.12 degrees. This is called decimal degrees, and decimal degrees technically could be as accurate as you could possibly want. You would just tack on more decimals to it. That's called decimal degrees. The degrees, minutes, seconds is very easy to change. Just type in your decimal degrees, and under the angle menu of the calculator, so you hit second and the apps key, it says angle above that. There's a function that has a triangle and then DMS. It means to convert that number to degrees, minutes, and seconds. So just hit enter and it will convert it. So 38 degrees, 7 minutes, and 12 seconds. All right, let's try this one. So just type in 225.8125 and second angle. Convert to DMS. So we have 225 degrees, 48 minutes, and 45 seconds. Now, occasionally there's one that you'll run into something that has enough decimal places in the decimal degree format where you would end up with, say, like, 225 degrees, 48 minutes, 45.21 seconds. You'll occasionally run into that. Generally, we don't allow that to have decimal points on the seconds. If you need the seconds to be more accurate, you just use the decimal degrees format. You don't put decimal places on the seconds. So it's generally uncustomary to do, although you'll see it, and it's not a big deal. It's just it's generally not customary. You usually just round it to the nearest second. But just in the homework, follow any instructions that you're given on rounding. All right, convert the following to decimal degrees. So we want to go the other way now. So if we have 32 degrees in 6 minutes, what does that equal in decimal degrees? Well, we type it in as we see it. So 32 second and angle. And if you notice, the first two options, you have a degree and then a minute mark. So you can just use those to type it in as you see it. So 32 degrees, 6 minutes. Then hit enter, and then it'll return it in the other format. So this was the same as 32.1 degrees. And then likewise, even if you went down to seconds. The only thing that's slightly different is, if you'll notice, there's no seconds listed in the angle menu, which I kind of find strange that they don't just go ahead and list it in there. But in order to get the seconds, you use alpha and the plus, which is a quotation mark, although the calculator knows to interpret that quotation mark as seconds in this situation. So this is equal to 126.429 degrees. And I'm just rounding to 3 decimal places, but again, follow any instructions in your homework or on test as to what to round to. Coterminal angles. If an angle measure is more than 360 degrees or less than 0 degrees, then it has an equivalent angle within the range of 0 to 360, and these two equivalent angles are called coterminal. If an angle measure is positive, you just subtract 360 until the angle value is within the range you want, so between 0 and 360. And if the angle measure is negative, you're going to add 360 until the angle value is between 0 and 360 again. So let me show you with an applet, how coterminal angles work here. Okay, so I have a angle that is in quadrant 1, and it's measured at 45 degrees. If I rotate this angle around, then eventually I can get the same angle measure, an equivalent angle. All right. Okay. In quadrant 1, I have an angle of 45 degrees. Now, if I rotate this angle around, then what can happen is I can end up with an angle measure that is the same angle. It represents the exact same angle, but it's outside of the range of 0 to 360. So in this case, 405 degrees. 405 degree angle and a 45 degree angle are called coterminal angles because They each represent the exact same angle. It's just that one of them is an additional rotation around the circle. So for instance, if you go around once, that gives you 360 degrees, plus an additional 45 degrees gives you a total of 405 degrees. So this is something that's coterminal with 45 degrees. And I could rotate around all the way around again and get the same sort of thing. You can rotate around as many times as you possibly could want. There's no bounds on angle measures for trigonometry. They can range from negative infinity to positive infinity. So here's another angle measure, 765 degrees. That's equivalent to 45 degree angle. It's just coterminal with it. If you rotate the other direction, so they start back at 45 degrees and rotate the other direction, you can very easily get into a negative angle measure. So notice here I have an angle measure of negative 140 degrees. But that is coterminal with, if I took 140 plus 360, and if I have an angle of negative 140, so rotated this direction, then that's equivalent to an angle measure rotated positively this direction by, if I took 360 minus 140, then that's 220 degrees. So this is equivalent to an angle measure that's positive 220 degrees. So actually, let me do this. Let me leave this on, and I'll take it over to 220 degrees. And you can see it's the exact same angle. It's just rotated differently. So that's what we mean by coterminal angles. And any angle that is outside of the range of 0 to 360 degrees has an angle that is coterminal with it, that is within that range. And you can always figure out what that coterminal angle is by just simply adding or subtracting multiples of 360. But one last thing to mention is if you have an angle measure that is within the range of 0 to 360, then it's coterminal with itself. So if you're asked a question, which generally this doesn't happen, but just in case, if you're asked a question as to what angle measure is coterminal with 220 degrees, you would just answer with 220 degrees. You're just looking for the angle measure that's within 0 to 360. So if it's already in that bounds, then just answer with the given measure. So let's take a look at a couple of example problems. So find the angle of least positive measure that is coterminal with each angle. 908 degrees. Well, save yourself arithmetic errors here, and just use the calculator is fine. Since 908 is larger than 360, you just want to subtract 360 until you get something in the range of 0 to 360. So in this case, 188 degrees. And that's your answer. The textbook will say that you need to figure out some multiple, the least positive multiple of 360 that will fit under the angle measure. So like for instance, what it's saying is 720 is the largest multiple of 360 that would be less than 908. You get the same answer. But for me, that's just a much harder way of thinking about it. I don't think in terms of multiples of 360, very easily. But I think very easily in terms of just repeatedly subtracting or adding 360. And that's perfectly fine. Now, if you get a measure that's, thousands of degrees, like if it's find a coterminal angle with something that's 2,900 degrees, it might take you a while to subtract all the 360s out. But a little trick you can use here is, let's say you want something coterminal with 2,900 degrees. So if you do this operation and hit enter, and then the next time just type in minus 360, it says here ANS minus 360, which means it's referencing the last answer that you put in. So the last answer you put in was 2,540. So if you hit enter, it'll give you that. Now, if you hit enter again, it'll just repeat the last operation, which is to take the last answer minus 360. And then at that point, you can just kind of, hit enter over and over until you finally get down to something within that range. So that's not a big deal. All right, negative 75 degrees. This is a negative angle, so we need to start adding 360 until we get into the range that we want. And in this case, the answer is 285 degrees. Lastly, negative 800. Now, that's not to say that if you know larger multiples of 360 in your head, like if you know 720 is the next multiple and you want to use that, you absolutely can. And it might get you to your answer a little bit faster. However you want to do it is okay. The final answer is the important thing here, finding the angle that is coterminal and in the range of 0 to 360.